السلام عليكم ورحمة الله، يعطيكم العافية شباب وصبايا، أتمنى الكل يكونوا بصحة وخير وسلامة يا رب. هلا راح نبلش بالheat transfer part which is it's very simple and short إن شاء الله. In chapter 16 we will talk about the different mechanisms of heat transfer. In the thermodynamics or the fluid mechanics part of this course or parts of this course, we talked about the heat as thermal energy. We talked about the heat direction of transfer, and also about the heat as quantity, whether it's in its energy form, rate of energy form, and so on. So here in chapter 16, we will talk about the mechanisms, how this heat is transferred with, or the modes, the mechanisms or modes. So the objectives here is to introduce the different or the basic mechanisms of heat transfer. So I remind you, the heat is it's a thermal form of energy. In thermodynamics, we were concerned about the amount and about direction in the second of thermodynamics. If you recall, the heat transfer deals with the determination of the rates of such energy transfer as well as the variation of the temperature. The three basic modes or mechanisms of heat transfer are conduction, convection, and radiation. Starting with the conduction, heat transfer is the transfer of energy from the more energetic particles of a substance or a matter to the adjacent, less energetic ones as a result of interaction between the particles or as a result of the molecular activity. In gases and liquids, conduction occurs in the form of collisions and diffusion of the molecules during the random motion, while in solids it occurs due to the vibration of the lattice that construct the molecules, and also due to the motion and the transport of the free electrons. The rate of heat conduction is controlled through a law called Fourier's law of heat conduction. It tells us that the rate of heat conduction is proportional to the cross-sectional area where the heat is transferred through, the temperature difference, and inversely proportional to the thickness of the layer. That's if we are talking about a plain wall. So the conduction, translate this into formula, it would appear as this formula here. So that proportionality is defined through this new parameter which is introduced here, the thermal conductivity. The thermal conductivity, which is a thermophysical property of the substance. So it's Ka times T1 minus T2. As we know, the heat transfer from the higher temperature region to the lower temperature region. So the temperature decreasing in the positive sense of the spatial dimension. So that's why the negative sign is introduced here. So the Q, the rate of heat by conduction, equals to minus times K times A times delta T divided by delta X, and the units of this heat rate, as we know from the previous parts of the course, is in watts. When the delta X goes to 0, then this equation, the delta T delta X, becomes a derivative, and this is the equation becomes in this form, which is well known as the Fourier's law of heat conduction. Again, this K is called the thermal conductivity. It's a parameter that measures the ability of a material to conduct heat. The temperature gradient represents the slope of the temperature curve on the TX diagram. The negative sign here to show that the heat is positive in the direction of decreasing the temperature. The thermal conductivity, here we check the thermal conductivity of some materials at room temperature. As you can see, for the diamond, it's very high thermal conductivity. The silver, 429, and the units for the thermal conductivity. If we check this equation, we will find that the units for the thermal conductivity is watt per meter Celsius or Kelvin, since we are talking here about temperature difference. So it's the same whether it's in Celsius or Kelvin for delta T, the same. Uh, let's check for the copper, silver. We notice from here that the good electrical conductors, such as the silver, the copper, are also good thermal conductors. Good thermal conductors. Here, the thermal conductivity has in the classification for different categories. So we can notice from this figure here that the materials that have the materials or the substances that have the highest thermal conductivity in general are the non-metallic crystals such as diamond, graphite, silicon carbide, quartz, and then it's followed by the pure metals such as silver, copper, iron, and then it's followed by metal alloys such as the aluminum alloys, bronze, steel, and it's followed by the category of the non-metallic solids such as oxides, rock, food, followed by liquids such as mercury, water, oils, and it's followed by insulators such as foams, wood, fibers, and the last, which has the least range of thermal conductivity values, are the gases such as hydrogen, helium, air, and so on. We can see that there will be overlapping, but this is the general trend. This is the general trend. The highest values of thermal conductivity, that's for the non-metallic crystals, then as we mentioned for the other categories. Here, explanation of how the conduction occurs in the gases and liquids, as we mentioned, through collisions and diffusion, while in solids through the lattice vibration of the molecular structure plus the flow of free electrons. We can see the effect of the let's say the when we have composite material or the alloy. If we consider the copper alone, we have the pure copper. We see that the thermal conductivity at room temperature is 401, but for the aluminum, for the nickel at room temperature is 91. For the constant alloy, we can see that which consists of 55% of copper and 45% of nickel, the value for the thermal conductivity reduces as much as 23, while copper and aluminum pure, they are 401 and 237 respectively at 300 Kelvin temperature, while an alloy of the commercial bronze, which consists of 90% of copper and 10% of aluminum, reduces to as much as 52 watt per meter Kelvin. Now in this table 16.3, it shows the effect of the temperature on the thermal conductivity. In general, for the solids, the thermal conductivity reduces with increasing the temperature, while for gases, the thermal conductivity increases with increasing the temperature, similar to the liquids as in the water here. Okay, now with thermal diffusivity, which is another thermophysical property, it's defined as the ratio between the conduction to the heat storage. It's not similar quantities, and that's why it's a dimensional parameter, and so it has units. So it's defined as the thermal conductivity divided by the heat capacity, the heat capacity per unit of volume flow rate. So that's rho Cp. The value of the thermal diffusivity for some materials are shown in this table here to the right. Now for the convection, which is the second heat transfer mechanism. So here we will talk about the second heat transfer mechanism, which is the convection. Convection heat transfer mechanism. The convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas surface between and the adjacent liquid or gas that's in motion. So two conditions are required: solid surface and moving fluid, whether it's gas or liquid. So it involves two or double effects or combined effects: the conduction and the solid surface and the fluid motion. The faster the fluid motion, the greater the convection heat transfer, and that results in forced and free convection. The forced convection, when we increase the motion of the fluid by external means, while the free convection, which occurs naturally. We will talk about this later. So here the forced convection, if the fluid is forced to flow over the surface by external means such as fan or pump or the wind, natural or free convection, it's due to the density variation that results from the temperature gradient. So if we explain here the forced convection, assume this is a hot egg and we want to cool it down, so we open a small fan on it to increase the heat transfer rate from the hot egg to the adjacent moving air. While here, if we leave the hot egg alone and let it cool down by simply the free convection that results from that, the the hot fluid will go up and be replaced by colder fluid due to the density variation that results from the temperature differences. Heat transfer processes that involve change of phase are considered as boiling and condensation, which are also considered as part of the convection regime. So the convection heat rate is controlled by a law called Newton's law of cooling. That's HA sub S times the T sub S minus T infinity. Here the sub S refer to the solid surface. The A sub S is the surface area, while this T sub S is the surface temperature of the solid. The H is a new parameter, is called the convection heat transfer coefficient, and according to this law, it has the units of watt per meter squared Celsius or Kelvin again, since we are talking about temperature difference. Typical values of convection heat transfer coefficient in general depends on the type of convection, whether it's free convection or forced convection, whether it's for gases or liquids, or whether it's the boiling and condensation, which is the convection when there's a phase of change involved. So the H value for the free convection of gases, it's in the range between 2 to 25. Free convection of liquids is in the range of 10 to 1000. For the forced convection of gases, it's in the range of 25 to 250. For the forced convection of liquids, it's in the range of 50 to 20,000. For the boiling and condensation, it would be the highest, as from 2500 to 100,000. Again, as we can see, there might be overlapping in values between these different sub-regimes of the convection. The convection heat transfer coefficient, it's experimentally determined, and it depends on many parameters such as the surface geometry, the nature of the fluid motion, the properties of the fluid, the bulk fluid velocity, and so on. The last heat transfer or fundamental heat transfer mechanism that we will talk about is the radiation. The radiation is defined as the energy emitted by the matter in the form of electromagnetic waves or photons as a result of the change in the electronic configuration of the atoms or molecules. So it's simply electromagnetic waves or photons that emitted by the matter. Okay, unlike the convection and the conduction, the radiation does not require intervening medium, so it can occur in the vacuum. It can occur in the vacuum, and the best example is the sun rays through the space that eventually reach the surface of the Earth. Okay, now for the equation, the maximum emitted heat rate from the surface is given through this equation, sigma times A sub s times T sub s to the power 4, and this maximum emitted heat is assumed by a black body. So the black body is an idealized surface that emits the maximum rate. Sigma here is a new parameter and it's called Stephen Boltzmann constant, and it equals to 5.67 times 10 to the power minus 8 watt per meter square Kelvin to the power 4. Here the temperature must be in Kelvin since it has the exponent, it's in the absolute scale, and since it has the exponent 4. It's not simply the exponent of 1 or a temperature difference like in the previous laws, Newton's law of cooling or Fourier's law of heat conduction. This law is called the Stephen-Boltzmann law that determines the maximum emitted heat from a surface. Now, for real surfaces, this amount is multiplied by a parameter epsilon, which this epsilon is called the emissivity. It's the ratio between the real surface to the ratio between the emitted thermal energy from a real surface to the maximum emitted by a black body. It's in the range between 0 to 1, where 1 represents the black body surface. Now, the value for the emissivity for some materials are shown in the table here. One in particular of special interest would be the human skin. We can see it's 0.95, which is relatively very high value, and that's a blessing. So we can keep the human body temperature, the internal human body temperature at its normal value. Okay, so that's why it required that this emissivity to be high. Okay, the absorptivity, it's another parameter. It represents the fraction of the radiation energy incident on the surface that's absorbed. So if we consider this incident radiation energy, which can be considered as the thermal energy coming from the sun. So if it hits the surface, part of it will be absorbed, okay, and that portion that's absorbed will be determined by this parameter absorptivity, while another part will be reflected, and it will be it's 1 minus alpha times the q dot incident. So part absorbed, part reflected. Okay. So a black body, it's a perfect emitter and it's also a perfect absorber. So the emissivity of a black body equals to 1. Also the absorptivity for a black body equals to 1. The absorptivity in general is in the range between 0 to 1, where 1 represents the black body. The net radiation heat transfer, if we have this is a general solid surface, and it radiates a heat, and at the same time there's also radiated heat into the surface itself. So the net radiation heat rate is given through this equation. This is the assumption that the surface has heat coming from the surroundings, which is as shown here. The surrounding may be simply the walls and the ceiling of a room, or the oven surface, the oven walls, or simply the sky, or simply the sky. So this is the emissivity, this is the Stephen-Boltzmann constant, this is the surface area of the body, this is the surface temperature of the body, this is the surrounding temperature of the body. Notice here that these temperatures must be in Kelvin units. In Kelvin units, they represent absolute temperatures. Okay, this is an example when if the surrounding temperature was equal to the free stream temperature of the moving fluid, then we may define a combined convection heat transfer coefficient that combines the effects of convection and and radiation. So the combined is simply the convection plus radiation convection heat transfer coefficient, where the radiation heat transfer coefficient is given through this relation here, epsilon times sigma times the sum of the surface plus the surrounding temperature times the sum of the square of the surface and surrounding temperatures. Now, these modes can happen simultaneously, and in practice, actually, always there will be two or more of these heat transfer mechanisms occur simultaneously. Okay, we'll consider examples about this. Okay, thank you. This ends the lecture of on the heat transfer mechanisms. يعطيكم العافية ونشوفكم على خير.